Hello, everyone. Welcome to our webinar. This session will be recorded for the people who are not able to attend this time, but definitely want to check our research and see what's happening further with AI developments. Feel free to address questions during the presentation in the chat, or just note them down for our Q&A section at the end of the presentation. Over the past few webinars, we explored the world of artificial intelligence and how different types of intelligent agents work and make decisions. Today, we'd like to share a short overview of the main types of AI agents and show how each one plays a part in building smarter systems that can learn, adapt, and assist us in everyday tasks. First, introduction about us. My name is Mihai Nagoe, and I'm the operations manager at Wayfair. I have a background in software development. I started in 2006 as a Progress developer. I've been using mainly Progress Open Edge and related technologies. So this year I'm having my 20th anniversary in this field. I have today with me Diana, and I will let her introduce herself.
Hello, everyone. I'm Diana Sherban, and I'm a software developer at Wayfair. I work on building software solutions and continuously improving my technical skills. Also, I've been especially interested in AI, and I explored how intelligent agents can help make everyday systems more efficient and intuitive, which brings me to the topic of today's presentation.
Thank you, Diana. A short introduction about Wayfair. As you can see, we have more than 13 years of experience as a company, and we support the full software project lifecycle from legacy to modernization projects. What makes us different is the top talent that we can attract from our two major universities that we have in town. Our core technologies evolve around Progress Open Edge and web technologies, a large number of our projects being focused on the modernization from Progress UI to modern technologies, Angular and React to be more specific. We have more other activities that we're focusing on, like the quality part, QA automation, and modern web and APIs. We're located in Cluj-Napoca, Romania, which is a growing IT hub, especially because we have those two major universities specialized in computer science. And we're proud that one of the universities is included in the EU AI Factory list, which will deploy new AI-optimized systems to further expand Europe's AI infrastructure. The raw AI Factory aims to acquire and deploy an AI-optimized supercomputer, provide a comprehensive suite of AI-enabling services, including HPC access, AI model development and training support, data space hosting, algorithm libraries, and tools for responsible and trustworthy AI. So we're really proud to be part of this factory. The agenda for today, we'll start with a brief look at how AI evolved over time, which will lead us to the concepts of AI agents. Then we'll explore the different type of agents, compare how they operate, and wrap up with some key takeaways in the short Q&A session. About AI agents, we humans make decisions all the time. Sometimes instantly, like pulling our hand from something hot, and other times after thinking carefully, or even after considering our past experiences and what we have learned. AI agents work the same way. Some react immediately, others plan ahead, and some even learn from experience, each with its own way of perceiving the world, making decisions, and learning from experience. Today, we'll take a closer look at how these agents evolved and what makes them intelligent in the first place. We will share our research on how these agents can improve the software development lifecycle with examples on each of the major topics that we considered. Each agent has its own way of perceiving the world, making decisions, and learn from experience. Um, for today, we built several agents that will cover the most common scenarios. They are built in Python, and we tested several major LLMs, both free and licensed versions. Before we dive into the different types of AI agents, let's take a quick look at how AI itself has evolved over time, from simple rule-based system to the intelligent agents we have today. There are different ways to classify the evolution of artificial intelligence. In research, you might find frameworks that define four main generations: information AI, agentic AI, physical AI, and even a speculative conscious AI. But for today's context, we'll use a more practical view, and we'll take a closer look at how AI evolved across these generations, from rules to learning and autonomy. So we have at the top we have AI 1.0. It all started in the 1950s with what we call now rule-based or symbolic AI. These were systems that follow strict logical rules, basically if-then statements. They couldn't learn or adapt, but they could simulate reasoning using predefined knowledge. Examples include early expert systems like Mycene or ELIZA. They were simple but revolutionary at the time. Then we have AI 2.0, machine learning. Instead of being programmed with every rule, systems started to learn from data. This made AI more flexible. It could recognize patterns and make predictions. Uh, think of things like spam filters, recommendation systems, or fraud detection models. These are all part of the predictive era. AI 3.0. We have the generative AI, which is where things started to get exciting. Instead of just analyzing data, AI could now create generating text, images, even code. This is the era of GPT models, DALI, Copilot, and other tools that assist us creatively. But even in this phase, all AI still needed our input. It waited for humans to prompt it. AI 4.0. Now we've entered the era of agentic AI. These systems don't just generate, they can plan, decide, and act autonomously. They can chain multiple steps together, access tools, and even collaborate with other agents to reach a goal. It's a big shift from assistance to autonomy. Think of systems like AutoGPT, Devin, or intelligent copilots that execute multi-step tasks on their own. And finally, AI 5.0, what comes next, is still speculative, cognitive, or conscious AI, a system that might have self-awareness or the ability to reflect and adapt on their own. We're not there yet, but it's exciting topic for the future of AI research. Now that we've seen how AI has evolved through different generations, let's focus on what actually makes these systems intelligent, the concept of an agent AI. AI agents don't just respond to commands. They can think about a task, decide what needs to be done, and take action on their own. They bring together reasoning, planning, and autonomy, which makes them quite different from traditional AI systems. Types of AI agents. We'll start with the simplest one to more complex ones. We have the simple reflex agent, is the most basic type of AI agent. They work like human reflexes. If you touch something hot, you pull your hand away. It works by reacting directly to what's happening around, using if-then rules to decide what to do next. These agents don't think about the past or plan for the future. They just respond to the current situation. For example, a thermostat is a simple reflex agent. When the temperature drops below a certain temperature, it automatically turns the heater on. And when the desired temperature is reached, it turns off again. It doesn't remember previous state or adjust its behavior. It simply reacts to the current input. Another example is an automatic traffic light system. It changes signals based on what sensors detect. For instance, the presence of cars, but it doesn't remember what happened before or plan ahead. This is an example of a simple reflex agent. This description is for an interaction with the database. Um, this is how it can be applied in a software development environment. After a simple reflex agent, the next step in complexity is the model-based reflex agent. The main difference is that this one doesn't just react to what's happening right now, it also remembers what happened before. It builds a small internal model of the environment, which helps it understand how things change over time. So when it receives a new input, it can combine that with what it already knows to make a better decision. These agents are more reliable in dynamic environments because they can use memory to avoid repeating mistakes or reacting blindly. But they still don't plan ahead or set goals. They just make smarter decisions based on experience. For example, think of a robot moving around the room. A simple reflex agent would just avoid obstacles as it encounters them, turning every time it hits something. But the model-based agent remembers where those obstacles were. It keeps track of its previous movement and uses that information to plan a smoother path next time, avoiding places it knows are blocked. This version of the agent works similarly to the simple reflex agent, but with one key improvement, which is a memory. It keeps track of what happened before, so it doesn't repeat the same mistakes. In this example, if a query fails in the previous session, the agent remembers that and suggests modifying it instead of running it again. A goal-based agent. Up to this point, the agents we've seen were mainly reactive. They responded to what's happening right now, or maybe use memory to improve their reactions. Goal-based agents take things a step further. They don't just react, they plan. They start from a clear goal and then evaluate different actions, predict possible outcomes, and choose the one that brings them closer to that goal. What makes them different is that they focus on future conditions, not just what's happening in the present. They reason, plan, and can just adjust their approach if something changes. So instead of simply reacting, they act with purpose. Every decision is made with an end goal in mind. A good real life example of this is a delivery drone. A simple reflex agent to just avoid obstacles as they appear, but a goal-based one goes further. It plans the entire route, predicts weather conditions, checks if battery has the correct level, and adjusts its flight path to make sure the package gets delivered on time. One of the implementations follows the same principle. Instead of just executing queries or remembering past actions, this agent starts with a specific goal. For example, generating an OpenAJBL program to find the smallest number in a list. We'll see this as an example, and we'll have another example for this, which is more close to the development lifecycle. We have then utility-based agent. This one goes one step further than just achieving a goal. It uses a utility function, a way to score possible actions and choose the one with the highest overall benefit. While goal-based agents focus only on reaching a target, utility-based agents compare different outcomes and pick the most valuable option. This makes their decisions smarter and more flexible, especially when there are multiple goals or trade-offs. A self-driving car doesn't just aim to reach destination, it constantly evaluates different factors: speed, fuel efficiency, and safety, and uses utility functions to decide which options offer the best overall outcome. It might choose a slightly longer route if that means safer driving or lower energy consumption. Um, we implemented the utility-based agent. One of the implementation focuses on error handling, and another one is focused on review. For the error handling, yeah, instead of fixing problems randomly, it evaluates each error based on severity or frequency and assigns the utility score, similar with the review. Learning agents represent the most advanced stage in this evolution. They don't just react, remember, or optimize, they improve. These systems learn from experience, adapting their behavior as they collect more data or receive feedback. The more they interact with the environment, the more accurate and efficient they become. In other words, they don't just follow a fixed set of rules, they rewrite their own rules based on what they've learned. In banking, fraud detection agents analyze thousands of past transactions, learn what suspicious patterns look like, and adapt as criminals change their strategies. Over time, they get better at catching fraud without flagging normal activity. One uh, implementation of a learning agent would be to check if a number is prime, and what we wanted to achieve as a next step is to try to migrate an open-edge procedure into an object-oriented framework, and have the agent learn from feedback. Okay, we're at the demo stage. I think everybody is excited about this part. I will leave Diana share the screen and show you the research we've done so far.
Okay. So now that we've seen the different types of AI agents and how they work, let's move to the practical part of the presentation. I will show you a series of demos where different agents perform real development tasks, such as code review, code generation, documentation, testing, and even migration. So the demos will start with simpler examples and then move to more complex and applied scenarios. But just a quick reminder, a goal-based agent focuses on achieving a specific objective by planning the steps needed to reach that goal, while a utility-based agent evaluates multiple possible options and chooses the most efficient or valuable solution. In the demo, we will start with two simpler examples, code review and code generation. After that, we will move to more practical scenarios like documentation generation, OA migration, code review for migration, and unit test generation. Before running the agent, it's important to mention that each agent is not working only with the AI model. Every agent also loads a knowledge base and a set of project conventions. The knowledge base contains information about OpenEdge ABL syntax, rules, and examples, as you can see in the following file. On the other hand, the conventions file, which is this one, contains project-specific rules like naming conventions, formatting, and best practices. This means that each agent reviews code not only based on general AI knowledge, but also based on specific project rules and coding standards. For the demo, we have a run.py file, which is this one, that acts as a launcher for all the agents. When we run it, we get a menu with all available agent demos, and from here we can choose which agent we want to run. We'll start with the code review demo, which is implemented as a utility-based agent. A utility-based agent doesn't just find errors. It evaluates each issue, assigns a priority score based on severity, frequency, and how easy it is to fix, and then decides which issue should be fixed first for maximum impact. Now, for our code review utility agent, we have the following example. First, we give the agent an input file. In this case, an OpenEdge ABL file that contains several intentional issues, such as naming inconsistencies, missing assignments, and structural problems. The agent will analyze this file as if it were reviewing code written by a developer. Now let's try and run, first of all, the run.py file. And here's how our menu looks. Then we'll choose to execute our code review utility agent, which is number 1. And it will start to execute and evaluate the input file. First, we give the agent that input file, and in this case, an OpenEdge ABL file that contains several intentional issues, such as I said, naming consistencies, missing assignments, and structural problems. After we provide the input file, the agent performs several steps. First, it analyzes the code and detects all the issues. Then, it generates fix suggestions using AI. Finally, it calculates a utility score for each issue and prioritizes them, so we know which problems should be fixed first. It seems like he encountered 7 issues, and let's see how our output file looks like. After the agent finishes the review, it generates a structured output report. In this report, we can see the file that was reviewed, the total number of issues found, the scoring formula, and then a prioritized list of issues. Each issue includes its rank, category, line number, a description of the problem, the exact code line, well, almost the exact code line, a utility score, and also a suggested fix. This is important because the agent is not only identifying problems, but also helping us understand what should be fixed first and how to fix it. What makes this output specific to a utility-based agent is the utility score. The score is calculated using multiple factors, in this case, severity, frequency, and fixability. So the agent does not treat all issues equally. Instead, it tries to estimate which issues bring the highest value it fixed first. Now let's take a look at our report and compare it to our input file. Let me show you first some of our naming conventions, because it seems like the highest priority ones are syntax issues because they have the biggest impact on whether the code runs correctly. And after that, we have some naming issues which are less critical from an execution point of view, but still important for consistency and maintainability. Now, as you can see, the first one of the issues, it is that we have a reserved keyword in ABL and it cannot be used as a variable name, the definition of this variable text. And then some other issues can be the fact that we have a missing period at the end of a statement, which is, I think, this one. But as you can see, the line error is not always the correct one. And that's what I wanted to show you. When we go to the naming conventions, we can see that we told our agent to use camel case, which is something that is missing here. So our agent was able to identify this issue and tell us about it and even a possible correction. The same thing happened for cast name and also for vcity, which is this one here, and also total amount, which is some of the applications of the naming conventions that we established with our agent. So we can say that we got a pretty good solution. Now, During development, we also encounter some challenges, of course. For example, sometimes the agent would detect false positives or occasionally report the same issue more than once. We improved the prompts and parsing logic to reduce these cases and make the results as accurate as possible. But like any AI-based system, it is not perfect and still requires human validation. Now, after the utility-based code review example, the next demo focuses on code generation. Let me close these tabs. This time, instead of evaluating multiple issues and choosing the most valuable action, the agent starts from a clear objective and works step by step to achieve it. This is why this example uses a goal-based agent. Now, let's try and run it first. We'll use, let me clear a little bit the terminal. Okay, so when we look at the menu, we will use now the code generation goal agent that generates ABL's code step by step from a goal prompt, which is number 2. Okay, a goal-based agent is centered around a specific objective. Instead of simply reacting to the current input, it plans a sequence of steps, executes them in order, and adjusts along the way until it reaches the final goal. For this demo, I'm going to use the following input. We provide the agent with a coding task, and based on that task, it has to generate the implementation from scratch. For this example, we have the following task. Create an OpenEdge ABL program that defines an array of 10 employees and displays a summary report showing average salary, highest paid employee, and their salary, and then the lowest paid employee and their salary. So you can see that we gave him a little more multiple small tasks, and let's see how he's able to plan everything. Just like the previous agent, this one also uses the shared knowledge base and project conventions from the base agent. That means that it generates code not only from the user's request, but also using ABL syntax knowledge and project-specific coding standards. Once it receives the goal, the agent first creates a plan by breaking the task into smaller subtasks. Then it generates the code incrementally, one step at a time, building on what was already generated. After each step, it validates the result and, if needed, tries to correct errors before moving forward. This is what makes it a goal-based agent, basically. The whole process is driven by a final objective. The agent is not just reacting to input, and it is not ranking alternatives like the utility-based agent. Instead, it decomposes the goal, follows a plan, and tries to complete the task successfully. So let's take a look at our output. We have two files. The first one is the one that he successfully generated, and the other one is the same solution, but we can also see the steps that he went to with. For example, this is the plan that he created. Define a timetable or array structure to store employees and salaries, then populate the array with sample employees data, calculate average salary, identify highest paid employee and identify lowest paid employee using loops, and then format and display the summary report with all three metrics using message statements. So what is especially useful here is that we do not only see the final result, we can also see how the agent reached that result, how it broke the task into subtasks, what code it generated after each task, and whether the step passed validation. So the process can be more transparent, so not just the final output. And as you can see, after each generated subtask, the agent validates the current code. So the first one is subtask did the following things. So basically, he defined all our employees, naming them and giving them a specific salary. And after that, he successfully validated the code. And after that, the step is marked as validated, of course, and if not, the agent captures the error output and uses it to attempt an automatic correction. But let's see if we had that step at some point. Then we have the second subtask where he creates the timetable and assigns to the timetable those values. Okay. And then we have the third. Each step is completed with the following subtask. For example, we had already have the definitions, and then for subtask 2, he managed to display us a message with the information that we have for now. After that, of course, here's the definitions, the message. We define our variables, and we try to calculate the total salary, the highest and lowest, and the average. Okay, and it seems like for the fourth subtask, I'm going to the end of the code, we managed to display also the summary of the report of our employees, which seems to be kind of correct. Now, the main advantage of this approach is that the agent works in a structured, goal-driven way. It plans, builds incrementally, validates, and self-corrects. At the same time, it still needs human oversight because the generated plan or the fixes may not always be ideal or as we want. Okay, so it seems like our goal agent did a great job. Now, let's move on to the next one. The next demo is more complex. And here is where things start to get complicated. We are going to introduce the learning agent. In this example, the agent is not only executing a task, but also learning from previous migrations and improving its behavior over time. The task in this case is to migrate a procedural ABL program to an OERA object-oriented architecture. Now let's talk a little bit about what is a learning agent, because it's different from the previous agents, especially because he is able to improve over time. It does not only execute a task once, but it also remembers mistakes, patterns, and rules discovered during previous executions and uses that knowledge in future runs. So instead of starting from zero every time, the agent is able to build experience and become more consistent and more accurate over time. Now, in this demo, the agent migrates a procedural ABL program to the OERA architecture, which separates the application into three main layers: the service interface layer, the business entity layer, and the data access. Now, for the input of our agent, we will use the following file. We have the OERA migration, okay, which is this one. Okay, so we have the following file, which is a procedure. Here we have a procedure to get active customers, then another one to validate a customer, save customer, delete one, and get credit status. Okay, so we have a few procedures. Now, the input for this agent is, as I said, is this procedural ABL program that contains multiple procedures. The agent will analyze this procedural code and transform it into an object-oriented structure that follows the OERA architecture. Let's try and run it. Okay, so if we take a look at our menu, our agent will be the OERA migration learning agent, which is number 6. Okay, so he will start its own process. The agent analyzes the procedural code, identifies data, access operations, business logic, and service level operations, and then splits the logic into the appropriate layers. As a result, it generates multiple classes: a data access class, a business entity, and a service interface class. What makes this learning agent a specific learning agent is the learning state. During each migration, the agent records problems, rule violations, and architectural mistakes that were detected in the generated code. These are saved in a learning state file that the next time the agent runs, it uses these learned rules to avoid making the same mistakes again. Okay, it seems like it's done. Let's take a look at our learning state. After multiple runs, this is how it looks. The learning state contains things like incorrect methods, signatures, layer violations, forbidden operations in certain layers, missing data sets, incorrect error handling, and other architectural rules. And over time, this file grows and the agent becomes better at generating code that follows the OERA architecture correctly. So we can say that the agent is not just generating code, it is actually building a memory of past mistakes and using that memory to improve future migrations. Also, during the migration, the agent does not just generate the classes once. After generating each class, it checks the code against the ORA architecture rules. If violations are detected, the agent can automatically attempt to fix the code and regenerate the class. This process may repeat multiple times until the code respects the architectural rules, which is why he detected so many issues here. Now, if we take a look at how our files look like, we have the business. Let's start with the include files. First, he attempts to define our theme table that we need for our customer with the fields that he considers that we need, and then, of course, the data set. And after that, he goes to our data access file, where we can see that he used the data set that he generated and of course created different methods like the create customer, update customer, delete, and read customer by ID. All of them are being used then in our business entity file. As you can see here, he uses the data access to run the business logic here. And after that, he also created our service interface file, which looks like this. And of course, it uses the business entity layer. If we take a quick look at how the files actually look like, you can see that are pretty consistent, even with the naming conventions and everything. Now, let's try and see if it can improve also by our feedback. For example, in the terminal, of course, he's done with his work, but he also expects some feedback from us. For example, let's say that we want to rename. Let's rename one of the methods. For example, save customer. Okay, so let's try and rename save customer into create customer. We'll tell him that I want to refine the B class and then rename the save. Okay, so let's say store customer. Let's rename from the save customer into store customer. And let's see if he's able to take in consideration our feedback. Okay. All right, let's close it and see if he. Oh, okay. So he did take in consideration what we said. So he changed from create customer to store customer. And in our learning state, he completed it with what we said. So rename business process names to use actual verbs. Okay, great. Of course, the output is not always perfect. I mean, the agent can still make mistakes, especially in complex migrations or when architecture rules are very strict. That is why it is important to always review the generated code and treat the agent as a development assistant, not as a fully autonomous developer. And even when the agent makes mistakes, those mistakes are useful because they are stored in the learning state and help improve future migrations. Now, let's move on to our next agent, which is the OERA documentation. Is also a learning agent. After generating and restructuring code with the migration agent, the next step is to make that code easier to understand and easier to maintain. That is where the documentation agent comes in. This example also uses a learning agent, but this time the task is not migration, it is a documentation generation. This is still a learning agent because it can store past lessons and improve the way it generates documentation over time. It learns from previous tasks, from issues encountered during generation, and also from explicit user feedback. Now, the input for this demo is a single ABL source file. In our case, we will use one of the classes generated by our migration agent. In this case, we'll use customer DA, which is this file. So this demo can also be seen as a continuation of the previous one. After generating code, we generate documentation for that code. The agent first performs a structural analysis of the ABL file. It detects classes, methods, procedures, functions, and parameters, including parameter directions such as input, output, or input-output. After that, it generates a first documentation draft automatically. Then, in a second step, it uses the language model to improve readability, add short descriptions, and make the documentation more useful for developers. Optionally, it can also accept feedback and refine the documentation further while storing lessons for future tasks. One important detail is that the agent does not rely only on the language model. It first performs role-based structural parsing of the ABL file, so the documentation starts from extracted code facts, not only from model interpretation. So first let me run and see how our agent works. We'll say that it is done. He will generate our menu, and then we can run the documentation learning agent, which is number 4. Now, the documentation, I think I already said, the documentation is generated in 2 stages. First, the agent creates a structured static draft from the parsed code. Then it enhances that draft with the language model to improve clarity and readability without changing the underlying technical information. Of course, if feedback is enabled, the agent can refine the generated documentation and even extract generalized documentation rules from user feedback, which are then stored, of course, in the learning state. Now, in this case, the learning state stores lessons about documentation quality. That can include previous issues, successful documentation patterns, and generalized rules extracted from user feedback. So over time, the agent is able to become better, not just at parsing code, but also at presenting the information in a clearer and more useful way. Okay, it seems like our agent is done. Let's take a look at what he was able to do. Now, this is how our learning state for the documentation looks like. We can see the goal, what he extracted, and some of the requirements that he has for the classes, procedures, methods, some rules that he has to respect. Now, let's see what he was able to do. Okay, so this is how our ABL documentation looks for the customer DA file. It contains the discover structures from the source code, such as classes, methods, procedures, and also functions. And together with parameter information, of course, and improved description. So we can say, if we take a look at our file, we can see what the information that he displays about each method, such as where he comes from, the description, what the parameters do, and also the return type. We can see that we don't have any procedures and functions. So, well, yeah, the result is a developer-readable documentation that can be reviewed, refined, and also reused. Now, the main advantage is speed, because the agent can generate documentation automatically from existing source code. Another advantage is consistency, since it extracts structures and parameter directions in a systematic way. Of course, the output should still be reviewed. And now let's move on to our code review agent, which is a utility one. After generating the OERA architecture with the migration agent, the next logical step is to review the result. Now, this demo shows an OERA code review agent implemented as a utility agent. The input for the demo is the set of classes generated by the OERA migration agent, which means that we are going to use for input the generated files by our migration agent, which are these ones. The review is based on multiple knowledge sources. It uses general ABL syntax knowledge, project coding conventions, and as the other ones, and strict rules for each layer. Now let's take a look at how our agent is able to work. We'll say for the documentation, of course, it is done. He will display us the menu, and then we will run our code review agent. We will get like the other one. If you remember, we already ran a code review utility for more simpler input file. But let's see what he's able to detect for our classes. Now, if we take a look, it seems like he's not done yet. Let's wait just for a little bit. It seems like it takes, oh, okay, he's done. So let's take a look at our output file. So we are looking at our OERA review. Okay, so this is how it looks. For example, for our DA, it seems like we have a runtime issue. Let me bring the input file. It will be easier to see those mistakes. It seems like he encountered for create customer the following issue: should use exclusive lock or create statement, but the statement itself is inside for each without proper transaction scope. Okay, now we have here another one declaration, which says that I think it used the conventions that we gave him, and it says that for read all customer, the parameter, which is true, the parameter is never used. It seems like we never use pfilter even if we declared it. So it seems like our review agent is able to detect some issues correctly. Now, the main advantage here is also speed, because the agent is able to detect the multiple issues maybe faster than we sometimes are able to, which is some of the advantages that this agent brings us. Now let's move on to the next one, which is the last one, and is the most interesting one. It's OERA unit tests, which uses a goal agent. Okay, so let's see. Let's run it. We have here the number 8. Now, the input for this demo is a class generated also by the OERA migration agent. For example, the customer DA class. The agent receives the source code of the class and a goal that describes what the test suite should do. The agent does not generate the entire suite in one step. Instead, it first creates a plan, then splits the work into smaller subtasks, generates code step by step, and then validates each step and finally produces the complete test suite. It seems like he needs a little bit more time. We are using also the customer DA, and our output will be revealed here. It seems like it needs some more time. We'll also have an execution log, just like for the other utility agent. And we will be able to see the internal reasoning process of the agent. It starts with the goal, then creates a plan, then generates the test class step by step. And after each step, it validates the result before continuing. And at the end, it produces the final test class. Of course, the output consists of a generated ABL unit test class and an execution log that documents the steps and the agent took to reach the log. Also, this approach is useful because it produces more structured results and makes the generation process more transparent, but the generated results should still be reviewed by a developer. Okay, it seems like he's done. Let's see our result. So this is how the whole class for tests looks like. If we take a quick look at it, seems like it's pretty much complete. Of course, he still needs to be reviewed by someone. But if you take a look at how our log looks like, I'm going to go on the top of it. Okay, generate an OpenEdge unit test suite for the following code. We have the code, the input, and then that's how our plan looks like. For example, create a test class file with proper ABL structure, define test helper methods, test method for create customer, update, delete, and then he starts creating each subtask. He generates the first one. Let's see, it seems like the validation passed, and then he starts with the second one. Here we have there's first one completed by the second one. Helper methods for the test data creation. And if we go at the end of it, we can see that the validation passed. Of course, if at some point he encountered an error, he will regenerate that specific task and try to get to a final solution. And at the end, we can see that all the validation passed, and this is the final result. Okay. Now, of course, he might make mistakes, and we should always review what the agent actually did. But it's a really quick start and maybe it might bring us closer to being faster when it comes to developing and writing tests. Now, across these demos, we saw different types of agents working together. Learning agents that improve over time, utility agents that evaluate and prioritize issues, and goal-based agents that plan and execute complex tasks step by step. So together, they just show how AI agents can assist not just with code generation, but with architecture, documentation, review, and testing across the entire development lifecycle.
Can we go to the code itself?
Sure.
Looking at them as well.
Sure. So now up to this point, we've seen what the agents do. Now I'd like to switch to the implementation. So let's see how it looks. But before looking at the agents themselves, we have a shared configuration file that I want to show you. and might help in implementation. This is how it looks. First, we define which LLM provider we use, such as Anthropic, OpenAI, or Grok, and the specific model that will be used by the agents. Then we define the paths to the knowledge base and project conventions, which are loaded by the agents and used as context when generating or reviewing code. We also define a default output directory, where the agents will write their generated files, although each demo can override this path. And finally, we have some general agent settings, such as the maximum number of retries for generation and the maximum number of tokens for model responses. Now, with the configuration in place, the next important component is the base agent, which is the foundation of all the other agents. All the other agents, the learning, the utility, and goal, inherit from the base class. This means that base agent provides the common functionality shared by all agents. The base agent is responsible for three main things: connecting to the language model, loading the knowledge base and project conventions, and then building the system prompt that is sent to the model. First, we have the base agent here is created and initializes the LLM client and loads two important things: the knowledge base and the project conventions. This will later be injected into the prompts sent to the language model. Next, we have this method, load knowledge, where we can say that the knowledge base contains general ABL knowledge, as I showed you, such as syntax rules and other technical information that helps the agent generate or review code accurately. Also, we have the conventions that does the exactly same thing with the conventions file. Now, here is where we build our system prompt, which is the most important method from the base agent. This method constructs the prompt that will be sent to the language model, and it combines multiple sources of information. The prompt is structured in two main parts: a static section and a dynamic section. The static one contains the knowledge base and project conventions, which do not change often. So the dynamic section, on the other hand, contains the current task, the agent role, task-specific roles, and any learning memory or context. Now, the reason for separating static and dynamic content is to support prompt caching. Large static content like knowledge and conventions can be reused across multiple requests, which reduces cost and improves performance when using certain LLM providers. So this is how our base agent looks like. Here is the static zone, where we give him the knowledge and the conventions, and then comes the dynamic zone, which is specialized on each one of the agents. And now let's talk about the most interesting, at least for me, one, which is the OERA migration agent. It is designed to perform procedural ABL code, transform procedural ABL code into an OERA object-oriented architecture. Unlike the goal, which focuses on completing a coding task step by step, or the utility, this agent restructures an existing procedural program into a layered architecture. The agent generates the full OERA stack. Shared timetable and dataset include files, data access, business entity, and service interface. Now, the OERA migration agent also uses learning state, which means it can remember architecture mistakes from previous migrations and avoid repeating them in future runs. The OERA migration agent follows a structured pipeline. It loads the procedural source code, it analyzes the source structure and detects database access patterns, it generates shared include files for timetable and dataset definitions, it generates the OERA layers, the ABA and CE, and if it validates each generated layer against strict layer contracts. If violations are found, it attempts to fix them automatically. It saves the generated files and updates the learning state, and optionally, it allows a feedback loop for manual refinement. Now, the main method of the OERA migration agent is the following one, execute task. Let me find it. It's here. This method orchestrates the full migration pipeline. Source loading, static analysis, include the generation, layer generation, validation, autofixing, saving the output, and everything else. This is the central method of the migration agent, just like execute task in the main pipeline, in the goal agent, and some other agents that I might show you. The difference is that here the focus is not on solving a coding task, but on transforming procedural code into layered architecture. A key part of this agent is that it does not rely only on general ABL knowledge from the base agent. It also loads OERA specific architecture knowledge and defines strict contracts for each layer. These contracts describe which happens, let me show you here. These contracts describe what each layer is allowed to do. The A is the only layer that may access the database. B contains business logic and orchestration, and the service interface is a thin entry point that delegates to business entity. This means that the generated output is guided not only by syntax rules, but also by architecture rules. And this is how our conversions look like.
Thank you, Diana. I'm looking at the time as well. Maybe it's the moment to take some questions. If there are any questions regarding the code or the implementation before we skip to the conclusion part. I see one question from Mike. Yeah. So basically, you're creating your own cloud code copilot windsurf. Where do you see the benefit? I may pick this one up. The idea is not to recreate, say what other IDEs or implementations are doing. What we're trying to do is to make agents work for us and replace some of the activities that the developer does. We actually use Cloud Code. In these examples, we use a license from Cloud Code, API, and what we do with our agents is to train them to solve a specific task, like solve a review, generate unit tests, and so on. So it's a layer, I would say, a layer on top of the other, of the models. And the idea is here that we can integrate these agents in the development lifecycle. Like you can put in a pipeline and run the agents when you need them. You migrate a piece of code, and then you have an agent, create unit tests, do the review, make the documentation, and so on. So we want to delegate these type of activities towards different agents. And of course, there are other ways to do this type of implementation, of course. And we're looking also at orchestration with Cloud. So yeah, there are some other ways you can solve this as well, of course. If there are other questions. Okay, maybe we jump to our last part.
I think we have another question.
Okay.
Should I read it?
Shoot.
Out of all these use cases, which one do you consider to have delivered the best results? I think the migration one, I didn't expect it to have some such good delivery of information, and I think it did a pretty well job. And also the agent that we used for review, as you saw, he really encountered the issues that somehow we told him to detect, like the one the ones from conventions name or knowledge. And the fact that we were able to use the review one on the results and output from the migration one, I think it's a good step into what comes next into AI agents, which is maybe orchestration and the fact that they will be able to work within them uh, without the human touch.
Okay, thank you for the question. Just to wrap up, yeah, our research, yeah, of course, try to make a first introduction in the different type of agents. Of course, the learning agent is the most knowledgeable one, and yeah, it has the most benefits. We wanted to see which are the different types of agents and how they can be integrated given different tasks. Here is the list of different features. Yeah, quick recap, and maybe just as a small conclusion here. Yeah, the agent, as Diana mentioned in her demo, still need the human review. So we had some good results. We tried with several models. We used Cloud Code, and yeah, to be honest, I think we had the best results using Cloud Code and using a license Pro from them. We tried also with Gemini. We tried with Llama. Yeah, there were some good results as well there, but for the code part, I think Cloud Code is the best for us at least, or maybe we connected the best with this model. Yeah, what we wanted to achieve with this research is to see a step further in how more automation can be added in the project. Like we took an example of a migration project, which is one of our uh, most encountered business cases. And then we thought, well, how can we make automation work for us with AI? And yeah, I think it's not a silver bullet now, but yeah, we have some positive results with learning agent and giving it more skills and more feedback to be able to generate or migrate a specific type of procedure in a context of a project. And of course, we have the additional agents. Once you generate the code, you want to review, you want to generate unit tests, and so on. Okay, if there are any questions. Well, if not, then I want to thank you for being here with us, and I hope yeah, you found our webinar useful and started some brainstorming. So we wait for you to contact us for any other questions. We're available on social media or LinkedIn. Thank you for being here, and see each other on our next webinar. Bye-bye.